Good morning, everyone. Thanks for coming. We'll get started in just a couple minutes.
Morning, everyone. We're going to give everybody just a few more minutes to join. We'll get started at 10:05. Before we get started, I'm getting some feedback from somebody's audio. Can everybody, if you're not speaking, please go on mute. All right. Good morning, everybody. I think we can go ahead and get started here. I'm Dan Schultz. I'm one of the chairs of the Environmental Flows Workgroup. And we'll just go ahead and jump into the agenda here. Valerie, do you want to share the agenda with everyone, please? Great. Just a reminder, this meeting is typically recorded. So please, while we go through the meeting, if you're not speaking, go ahead and keep your mics off to make sure everybody can hear it good. As far as introductions and housekeeping, since these are largely been remote, we don't go through significant introductions as well as with the number of folks that we do have attending. But it is always helpful for everybody if you do have an affiliation to add that to your name so people can see what your affiliation is when you do speak or if you have questions. Sorry, I was just catching up a chat here real quick. If you have any issues with any of the audio or anything, please let us know. We'll make sure to get that figured out. Other than that, I didn't have anything else for introductions and housekeeping. As far as the agenda goes, the first item will be discussing a little bit about the work group name. And then we have a couple presentations, one on low flow metrics and stream classifications, followed by the Pewter Creek case study. And then we'll go into the updates on in-stream flow efforts as a kind of round robin for all the participants. And then we'll go ahead and wrap up and agenda items for next meeting. At this point, before we jump into the agenda, I always want to provide an opportunity if there was anything that anybody wanted to add to the discussion today. If so, if you want to raise your hand, I'll go ahead and call on you. All right, not seeing anything at this point. If anything comes up at any point during the meeting, just let me know and we can discuss adding it. I think we'll have time today to add any additional agenda items. So the first item I have here is just a potential work group name change. This comes from the way that we define terms in the California Environmental Flows Framework. In particular, the difference between the term ecological flow criteria and environmental flow requirements. Right now, we're considered the environmental flows work group, which is more of a implementation component. And a lot of the Water Monitoring Quality Council's alignment is more with sharing data and information that helps support implementation, which would line more up with the ecological flow criteria component. So the question here is whether we want to keep the environmental flows work group name versus ecological flows, switching it to ecological flows, which would align a little bit better with the Water Quality Monitoring Council's goals and objectives. So I don't know if we were able to figure out, my fingers are crossed, that we can put this as a poll. But also, before we start the poll, I wanted to open it up to anybody's thoughts or comments on a potential name change along those lines. Norman.
Dan, I think, can you hear me okay? I think some of us might be having audio problems this morning. Can you hear me?
Yes, I can.
Okay. I personally think that the wording environmental flows it's not a widespread term in the common layperson's lingo, but I think in the scientific communities and the aquatic sciences communities, it carries a certain amount of meaning that is just general enough. But I think it's a good name, frankly, regardless of exactly what the terminology within the framework is. I mean, the framework, I guess, is not a product of this work group, but this work group allowed that framework to mature. I don't know. I think the name's fine. Is my personal opinion.
Okay. Yeah, one of the thoughts that I had with it was we seem to get hung up a lot on the regulatory implementation of environmental flows, which is not the intent of this work group. And so I had a little concern that the nature of the name was leading more towards people thinking that this work group was focused with the regulatory outcome, which, I mean, ultimately that is a goal. But really from the Water Monitoring Council standpoint, it's a little bit more focused on non-regulatory efforts. So that was the only concern I had with the concept environmental versus ecological. So I'm gonna go ahead and assume here that we're still trying to figure out how to do a poll. And does anybody else have any other comments or thoughts on the name?
Yeah, and there's some comments in the chat.
Oh, thank you. Popped up. Looks like we have a couple different things. What about ecological flow or flow ecology? I think, yeah, it would be the thought, John, would be that it would be, if we went for a name change, it would be there what we have or California Ecological Flows Work Group. And I think,
Dan,
and Valerie,
the
you'll
poll
have to
is,
help me.
can you hear me,
If you
Dan?
click on that, yeah, if you click on the forms
Oh yeah,
in the
the
chat,
poll is
does that
ready
take you
whenever
to the
you're
poll?
ready to launch.
Okay. Well, does anybody else have any other thoughts or comments that they want to share? Okay. So it looks like the poll is up. If everyone wants to go ahead and do a vote, we'll circle back, maybe give everybody plenty of time to do so. We'll circle back maybe in between our two presentations we have today, just to discuss any results. So with that, I know we're ahead of schedule here. Is Jesse on? Double check. Jesse, if you are on, we're not hearing you. Let's see, is Ethan on?
Hi, Dan. Yeah, I'm here.
Ethan, would you be up for swapping positions with Jesse, since while we figure out if she's joined or her audio is having issues?
Sure, I could go ahead.
Okay, so we'll turn it over to Ethan here to present on what we've titled as Pewter Creek case study.
Thank you. All right. Can everyone see my screen? Could I get a thumbs up from someone, or you can see that?
Yep. Yeah, we can see it.
Great, thanks. So my name is Ethan Baruch. I'm a senior environmental scientist with CDFW. And as Dan said, I'm going to share some results from a case study relating functional flows to the native fish community in Pewter Creek. So, we all know that environmental flow science has come a long way in recent decades, and there are now plenty of examples of environmental flows being implemented worldwide. However, there's actually very little evidence that implementing environmental flows regimes has led to significant positive outcomes for biodiversity. And one of the primary reasons for this is the lack of long-term environmental monitoring following the implementation of environmental flows. And a recent review of factors that are necessary to enable successful environmental flows implementation highlighted a stream here in California that is one of the few examples of effective monitoring of ecological outcomes following a change in stream flow management that was specifically designed to benefit the environment. So that'll bring us to our case study for today. It's Pewter Creek. If you're not familiar with the system, the headwaters up in the coastal range. Pewter Creek is impounded by Monticello Dam, forming Berryessa Reservoir. The stream then flows down to this Pewter Creek Diversion Dam. And then below that, we have Lower Pewter Creek that then flows down through the Yolo Bypass. And environmental monitoring Pewter Creek began in the early 90s. In this study, I analyzed 25 years of data from annual fish surveys at 4 sites below the diversion dam. So starting right below this dam, down to about 21 kilometers downstream of that. And just kind of looking at effects of damming on this river, these are hydrographs from, on the left, we have upstream of the upstream of Lake Berryessa. So this is a unregulated portion of Pewter Creek. And we see a very typical hydrograph for streams in this part of California that are rain dominated. We have high flows in the winter and very low flows in the summer. Downstream of this diversion dam, we have flows that look pretty different, right? We have a hydrograph that is not totally representing what we would expect it to look like in a natural system. So other than having a large dam, the thing that makes Poudre Creek a very interesting case study, of course, is the Poudre Creek flow accord. Some of you have probably heard of this before. And there's a really long history of stream flow management for multiple uses in Poudre Creek. And I'm not going to go into those details here, but just in summary, following some really low flows and a large fish kill in 1989, the Poudre Creek flow accord was implemented in the year 2000. And this is a court-ordered flow accord that contains three primary flow objectives or flow requirements that were specifically designed to benefit native fish species. So these include a fall pulse to attract anadromous species, a spring flood pulse, and sustained spring flows for outmigration, recruitment, and juvenile rearing, and then minimum dry season low flows to prevent stream bed drying. And so we can look at the relative abundance of native fish in this stream, and before the flow accord, there was fairly low abundance of native species in this system. There were a few wet years right before the flow accord was fully implemented. And then following 2000, we have this really sustained high abundance of native species in Poudre Creek. So that's pretty great. Several other studies have looked at this and kind of found this result. So what else could we then need to know about the change in the fish community in the stream? Well, what's kind of missing from previous analyses of the Poudre Creek fish community and really studies on ecological responses to environmental flows much more broadly is understanding which components of the flow regime are responsible for causing these observed changes. Several pieces of the flow regime were changed all at once. So what could have been contributing to this benefit to the native species that we observed. So then using this case study of Poudre Creek, I then tested if the functional flow metrics from CEP that have been hypothesized to support native species are actually linked to their observed recovery following the implementation of an environmental flow regime. Second, we also wanted to look at how the trajectory of the fish community might differ under alternative flow regimes. So, comparing how flows in the pre-accord time frame could have been, affecting and having different influences on the fish community. So probably everyone has seen this figure quite a few times before, but as a reminder, CEP has these 5 functional flow components that describe components of this flow regime that are known to support biological and physical processes that sustain healthy ecosystem function. And each flow component can be measured by these flow metrics, which quantify the magnitude, timing, duration, frequency, and rate of change of stream flow in each of these components. So what we want to do here is, again, look at variation in the fish community over time. So just kind of really brief high-level overview of the fish population models that we used here. We took data from these 4 sites on Poudre Creek and used time series models that account for observation error. Because we know whenever we go out and take any sort of measurement in the environment, there's always going to be some sort of error associated with that measurement. So we're trying to account for that variation. Also, time series models will leverage the temporal autocorrelation between years. So that way we can really try to identify how differences in flow are affecting fish and take advantage of the fact that we kind of know what the fish assemblies look like in previous years to inform how those flows are affecting the fish community. So kind of at the end, our main focus here is, again, to understand the effects of these individual flow metrics on this fish assemblage. this assemblage as a whole. So not just looking at fish at, each of these individual sites, but this kind of whole community in Poudre Creek. And trying to understand if these functional flow metrics are affecting population sizes of the fish species. We could also alter this model a little bit and test the assumption that all native species, so let's call these bluefish over here a native fish assemblage. Maybe all of these species respond the same way to flow metrics, and all these non-native species, these redfish over here, maybe they also respond the same way to these flow metrics. So then we could possibly ask this question, can any of these flow metrics be managed to benefit the native assemblage as a whole, instead of trying to pick and choose target species just to focus on individually? So jumping into some of these results, we ended up finding that those models that I just described that assume flow metrics have the same effect on the entire native assemblage and the same effect on the entire non-native assemblage actually performed better than models looking at individual species responses. So those are the responses. Those are the responses and the results that I'm going to focus on here. So, for example, the dry season duration, we found that a longer dry season, so a greater value of this duration, was negatively associated with the native fish community, but had a positive effect on the non-native community. So longer dry seasons tended to benefit non-native fishes and be detrimental for the native fish community. If we go through all of these flow metrics that we looked at here, we can see, so for example, this fall pulse magnitude, a greater magnitude of the fall pulse had a positive effect on the native fish community, but wasn't associated with any of the variation in the non-native fish community. The wet season also was pretty strongly associated with both the native and the non-native communities. The wet season 10% percentile magnitude, so kind of the base flow in the wet season, and the median magnitude of flow in the wet season, both showed that greater flows were beneficial for native species and detrimental for the non-native fish community. So these are some pretty useful results here, thinking about how flows we're seeing really that anytime we have a relationship between both a native and a non-native community, they're kind of in these opposite directions. So maybe these flows can be managed to specifically benefit natives and also maybe try to control our non-native population if that's what we're trying to look at here. So this is kind of one component of these results, but that's really showing just that the fish community was associated with these different flow metrics and how increasing or decreasing metrics might influence them. But we could look a little bit further at how the trajectory of this fish community could change as we alter hypothetical flow regimes. So to look at this portion, I use this metric which is called a quasi-extinction risk. So this is the likelihood that the population would decline by greater than 80% over the next 10 years. And this is a metric that's used by the IUCN to identify species at high risk of extinction. So what I did here is I ran many different flow scenarios that had different targets of each of these flow metrics spanning the observed range of each metric. So here, for example, the dry season duration, if in one of these scenarios I targeted a 150-day long dry season duration, I would project the native community's population over the next 10 years under a scenario where on average there was a dry season that was 150 days long with some variation around that, and then quantify the probability that the native fish community would then experience this really large decline. So looking at this result, the result of kind of this modeling scenario, we see that when we have shorter dry seasons, we have a low risk for the native species. So low risk is going to be obviously better. But as we're increasing the duration of this dry season, the likelihood of collapse in the native community is really starting to increase. In at least 1 year, there was a dry season that was 350 days long. This was observed in the record. So, pretty much flatline flow for an entire year. And sort of unsurprisingly, if you repeat this for 10 years, you're highly likely to experience a substantial collapse in your native fish community. But what we can do here is we can look at a scenario that targets the median value of the dry season duration before the flow accord went into place. So we can see there was a fairly high likelihood of declines in the native fish community at this kind of target value. But if we look at the median duration of the dry season following the flow accord, the dry season got shorter, and there was also an associated decrease in risk for the native fish community. Finally, we could take a look at the predicted natural value of the dry season duration. So this natural value is one of the products of kind of the CEF group. Anyone can go online and look up the predicted natural values of these streamflow metrics anywhere in California. So we took this information for this specific location, and we found that if you continued to decrease the duration of the dry season towards a value that is closer to this predicted natural range, you're going to continue to see a decrease in risk for your native fish community. We can additionally look at our non-native fish community. Prior to the flow accord, the native fish were doing pretty well. We saw that in the abundance data. Following the flow accord, dry season got a little bit shorter, and this was associated with some decrease in some increase in the risk for the non-native fish community. And this risk continues to increase if we're managing, again, for a more natural value of this dry season duration. In this exercise, we can really test exactly, what was driving these changes past kind of stream flow, but we can think about how flow is associated with the life histories of these species. So in this kind of natural hydrograph, we have a dry season that kind of follows this descending limb of the spring recession that has these pretty low flows. In this kind of more modified system, we have flows that are flatlined for a really large portion of the year. But we know that these native species are adapted to seasonal low flows and transitions characteristic of California streams. So several of the species in Poudre Creek have fairly discrete and short spawning periods, kind of in the spring recession timeframe, kind of towards the beginning of the dry season. Whereas if you kind of eliminate this recession and kind of start kind of early flows earlier, or if you just kind of increase the length of this dry season, you're really kind of decreasing these kind of cues that these native fish are adapted to. Whereas in contrast, a lot of the non-native species in the stream are from the Mississippi River Basin. They do really well. They spawn in these kind of warmer months with very stable flows. So as you're extending the time frame of these stable flatline flows, you could potentially increase the spawning duration and get multiple spawning periods for these non-native fish. So then kind of following that, looking at the magnitude of the wet season, looking at median wet season magnitude, we see that lower flows in the wet season were generally associated with higher risk for the native fish community and lower risk for the non-native community. So here, the flow accord didn't really change the magnitude of the wet season particularly much, but what we see is similar to the last result. If we keep modeling, changing this model to look at scenarios that are closer to the predicted natural magnitude of the wet season, we see continued decreased risk for the native fish community and higher likelihood of declines in the non-native fish community. So again, just kind of looking at what happens when you truncate this difference, this kind of natural value, this natural range of flows in these California streams, we're losing a lot of these high flows in the wet season that allow for migration passage upstream, access to floodplain, habitat, and resources that just aren't available at lower flows that these native species are really cued into taking advantage of. And you lose a lot of that once you truncate that that variation in stream flow. So the final result that I want to just look at in detail is the fall pulse, because this was one of the main focuses of the flow accord. And prior to the accord, most years did not have a fall pulse. So this was, in the modeling scenario, was a median magnitude of 0. But the flow accord mandated a 5-day fall pulse that occurred every single year. And on average, that was about 85 CFS for 5 days. So this is a relatively small amount of water that is being used during this period of time. But we see that this is associated with a potentially substantial decrease in risk for the native fish community. And again, we're seeing that if we keep managing for more natural values of flow, that is predicted to be associated with lower risk for the native fish community. So again, these are kind of the 3 examples that I want to focus on today, but for all of the flow metrics that were associated with the native fish assemblage, more natural values of these metrics were predicted to be associated with lower risk for the native fish community. So sort of the take-home messages here are that these functional flow metrics were actually able to predict fish community change over time fairly well. And there really isn't much other documentation supporting association between fish and functional flow metrics. So really that we're seeing that we can restore some ecosystem functions in a regulated stream. We also see that natural flows could potentially be used to inform environmental flows, and that that could be something to consider when looking at these sorts of flows. Finally, I do want to point out, some of you might have noticed that in those maps I was showing earlier, I focused this analysis on 4 sites that were that were the closest to this diversion dam. But there are 2 additional fish sampling sites further downstream that I did not include. And the reason for that is because the fish community really didn't change very much following the flow accord at these more downstream sites. And that's likely because these the physical habitat there is pretty highly degraded. And the habitats are just altered to a point where flows aren't really going to be affecting the fish in the same way. So this is just kind of highlighting the importance of section B and the reality that in some of these altered systems, even if you were putting down natural ranges of stream flow, you're not going to be able to support the intended ecological functions that you're trying to achieve. You need to look a little bit further. Again, kind of take a look at that section B. So that is kind of all that I wanted to discuss, but I hope we've got a little bit of time, I think, for some questions and any other discussion we want to look at today. Thanks.
Thank you, Ethan. Any questions? Comments? Jessica.
Hi, Ethan. My name's Jessie Maxfield. I'm the Water Rights Coordinator for the Bay Delta region and also the FERC Coordinator. I was just curious if your study includes any recommendations for modifications to the current flow regime that the Accord recommends.
No, that's a good point. This is a modeling exercise. We're looking at trying to find some support for these functional flow metrics. This is a very, very complicated system in Futter Creek. We're definitely not recommending any changes. That's not what we're intending to do here, just kind of looking at kind of, again, supporting that the function flow metrics are associated with response in the fish community.
Okay, thank you. Yeah, the reason I was asking is the Monticello Dam is coming up for relicensing. And so there's an opportunity to kind of provide some input on any additional studies or things that should be done in the creek, you know, to learn more about any potential changes to the current flow regime there. So I might be reaching out to you to talk to you more about that.
Sure. Thanks.
But thank you. I enjoyed your presentation. It was really interesting.
All right, look, next up is Tapa.
Hi there. I'm rather new to this kind of study, so maybe my question would be, you know, so, but anyways, I wanted to, you know, the things that you did upstream and the downstream, these flows that you show, is there a particular reason why where the regulated flows are the way they are? Is that required for certain things, or could one alternate the regulated flows to look more somewhat similar to the unregulated? Is that a possibility?
Right. Yeah, that's a good question. In this stream in particular, the Poudre Creek flow accord, it's a court mandated flow accord that was going to put into place in the year 2000, and this was a result of lots of negotiations, litigation for multiple water uses in the system. So it was kind of put in place by working with a lot of different groups, and it's not something, again, that we're at least with this study looking at adjusting, but they did put into place these three requirements that were intended to benefit native species. So that is something that they changed and that we found was associated with benefits for the native fish community, which is, again, kind of one of the main targets of this flow accord.
Oh, because you showed some, you know, another plot where you showed these yellow lines regarding the times when they, you know, they are not in match, and that seems to influence the fish, native fish population, right?
Right. You know, kind of the nature of water in California and probably most places is that there are lots of needs for it. So, you know, we're kind of showing that, just trying to show how these flow metrics are associated with fish. And again, that's not really the intention here to make any sort of recommendations.
Yeah, no, I understand. Yeah, so in a sense, like what you're calling native fish population essentially is for the unregulated flows. And so the other fish population, the non-native that you are seeing, is probably native for the regulated flow structure, right?
I think kind of what these results are showing that kind of restoring some more natural ranges of flows tended to be beneficial for the native fish. Is that
because they are kind of optimized for that flow structure, but the non-native ones are probably optimized for the structure that you get after you know, regulation.
Right. Yes.
Yeah. Thank you very much.
All right, and Norman?
Nice presentation, but I did want to ask if you could describe a little bit more about what you describe as fish assemblage. I've heard, you know, and even if you read the CEF document, I think you could say that certain functional flow components are, you know, envisioned to benefit fish, what I've generally heard described as guilds, and it might be a bunch of different species, but they have similar habitat or life cycle requirements in terms of where they spawn or where they feed or where they hang out just to conserve energy, you know, like in deep pools or shallow riffles and so on. Are your assemblages more or less equal to guilds, or is this something different?
Right, yeah, good question. So here I just grouped all all species that were native to this watershed as the native assemblage, and then all species that were introduced as this non-native assemblage. You could certainly do a deeper dive into guilds or different kind of functional groupings of these fish. Looking at kind of like the functional traits of a fish community and how kind of those traits are associated with different flow metrics is, I think, a really interesting area of work. That's just not something that we did here. Just trying to keep this study relatively focused and kind of more simple, but there's certainly a lot more you could look at.
Thank you.
All right, turning over some questions in the chat here. From Kimberly, it seems like we have seen dam operators seek changes due to some event, rain or drought. This seems to put fish on lower priority. Should they restrain from changing and granting these emergency requests?
Again, I think that is outside of kind of the scope here. So I'm not gonna get into any sort of kind of discussion of that one. It's
question from, and there's a couple questions along these lines here, Ethan, about publishing and sharing presentations or information that you've provided today with others.
Yeah, so the results from this are, we wrote this up in a manuscript that's currently in review. Hopefully that will be published in, not too long, and we can certainly share that manuscript once it comes out. And I think these meetings are recorded, so there's always the option to look back and rewatch anything. And again, once the manuscript is published, also all of the data associated with it are also going to be freely accessible online. So that is also going to be available for anyone.
Great, thank you. And I assume we can post this presentation, a PDF of this presentation on our website?
Sure, yeah, I can send that.
For availability? Okay. There's a question, how are non-native fish populations managed to allow native fish populations to increase? And I think a lot of your presentation went over that question, but I don't know if you have anything to add.
Yeah, so I think kind of, the way a lot of these specific requirements of the flow accord were designed were in coordination with some of the, major fish experts in California. So they were designed for, what we know about native fish and their life cycles to help support that. Kind of what we were showing here is that the kind of pulling these apart and actually, quantifying these relationships and showing that, in fact, that the native species did respond in one way to these flow metrics, often in the direction that the flow accord, changing them as they did in the flow accord was shown to kind of benefit the native species. And also tended to be detrimental for the non-native fish species. I can't speak to exactly what they were, trying to achieve if controlling non-native species was how that played into the accord, but this is showing that that was kind of one of these results.
Right, and then circling back, looks like we have two more questions from the audience here with Chris Milan.
Yes, Ethan, sorry if I'm making you repeat. I struggled to get on to the Teams and I'm late. So if you covered this, I apologize. But your October 1 to July 28th timeframe on the graph, I'm asking what years does this cover? What years does this cover?
Okay, great. I don't think I actually explained that particularly well. So these figures are dimensionless hydrographs that average stream flow. I believe this is over 40 years. So this black line is kind of this median value of flow. The water year starts on October 1st, so that's where we're starting here. So
Right.
this black is the median value. Then this is the I want to say 20th to 80th percentile. But yeah, these different colors of blue are kind of the percentiles of flow around that median value. So yeah, this is
Okay.
not presenting any year in particular.
Okay, 40 years. Okay, thank you so much. Helps.
And here from for folks that might not know the definition correctly, and correct me if I'm wrong, the dimensionless concept is to look more at patterns than just magnitude itself. So in other words, you can compare a gauge that is in a location that has lower flow magnitude to a gauge that's downstream that might have higher flow magnitude, and just kind of pick out the patterns of how flow is moving through the system.
Right, thanks. That's a good description.
Okay, and
Oh, one more
song?
question.
Oh yeah, go ahead, Chris. One more for Chris, and then we'll move on to a song.
Yes, the low flow period. So the late summer, is that included in the graph?
Yeah, so that's just kind of, you know, how these graphs are cut. But again, we're going through here's July, then ends up, you know, going out through October. So it's just that's
Okay.
split across water years.
Uh-huh.
Kind of the analyses we wrap those dry seasons into one, but that's kind of yeah, just visually here. That's how we cut the year.
But it is in the data.
Yeah.
Yeah. Okay. Thank you.
All right, what song?
Yeah, is it sound check, please, Dan?
Yes.
Yeah, thank you. Ethan, thank you for the nice presentation. So I guess my question might be a little complicated, but just let me just go through this step by step. For this flow provided by the Pura Creek Accord, and in comparison to the pre-accord period, and then the total volume of on average provided to the downstream locations, how much, like in terms of percentage of, say, unimpaired flows or natural flows, say given the total volume, how much would that be?
We didn't look at natural or predicted natural total annual volumes of flow. That is not something that's kind of included with these predicted natural values of flow metrics. So kind of we did not really look into total annual flow volumes. Again, kind of looking more at the these flow components that are part of SEP that are designed to support ecological functions,
Right.
even in hydrographs that aren't, maybe providing the full volume of flow for that you might experience in a natural system, still supporting the functions that these types of flows would provide in different seasons.
Yeah, Ethan, I was basically asking with the pretty much the code flows, like Pura Creek code flows that's added to the system. How much would that be in terms of total volume against, say, as I said, unimpaired flows? Do you have like that guesstimate of a percentage of like a 10% of additional flows overall has been provided to the system or something like that? Or do you have any idea?
Yeah, that's a little bit of a complicated question.
Yeah.
The flow accords went in place in 2000, and then after that we had kind of some extreme drought periods.
Right.
So kind of just flow volumes varied just given kind of different types of water years that we had. And again, the focus was more when that that flow was released. Again, we didn't really dig into total flow volumes. If you wanted to send me a message, I could probably look those numbers up for you, but that's just not something I have off the top of my head.
Yeah, I'm just saying it. I heard that the numbers, like a percentage of unimpaired flows that was provided for the code was like ranging from 5 to certain number of percentages. So I just want to make sure that whether you have certain numbers that could be provided.
Yeah.
And I guess a follow-up question also was sort of related to that, and I was thinking for the extinction risk that you talked about, there are varying numbers for the different parameters or flow parameters, and I was thinking, what would be the acceptable risk of extinction that we might look into from moving forward, and then to that is what would be the expected volume that should be provided in terms of, let's say, overall, again, sort of same layer of question of what proportion of unimpaired flows that should be or could be provided to get to that lower extinction risk. I hope I'm not making too complicated.
I mean, I think that's a really good question. That is, I think, really the focus of a lot of environmental flows is kind of what outcomes would you like? What's an acceptable range of risk, or kind of acceptable, kind of target to aim for your different flows. Kind of the hope is that this information could inform some of those discussions, but I think that really depends on what the water users, or the people who are managing a system, are trying to aim for. That's not kind of an acceptable risk. Isn't something that, again, I was trying to define in this study. That's really not where we were looking for this study, but I think that's kind of important in broad discussions of environmental flows. Yeah, and again, if you have more questions, please send me an email. I'd be happy to discuss further.
Thanks, Ethan.
All right. Thank you, Ethan, for your presentation. We'll go ahead and follow back up with our poll real quick, and then we'll turn it over to Jessie for her presentation. Let's see, give me just a minute to find the poll. So it looks like we have 56% to keep the current name, 43% to change it, although everybody didn't vote. So I'll leave it open for the rest of the meeting in case people didn't get a chance to vote. But as of now, we'll go ahead and be planning to keep the current name unless something changes by the end of the meeting. So now I'll go ahead and turn it over to Jessie for a presentation on low flow metrics and stream classification.
Thanks, Dan. Can you guys see everything? Is it working?
Yes, we can see it, and your audio is good.
Okay, thank you. Hi, my name is Jessie Ayers. I have been working with Ethan and a couple folks as well on this project, a counterpart to what Ethan just showed, funded by the CDFW. Looking more on the hydrology side, so Ethan gave a really nice presentation of how the flow metrics can be used to understand the fish populations. I'm going to focus more on the hydrology and specifically the low flows aspect. So differences in both intermittent and perennial streams and how low flows, how quantifying low flows in these systems can be important for these types of analyses, looking at specifically alteration from natural conditions. So we hear a lot that streams are drying up, climate change is causing changes to our low flows. And in addition, in California, we have a lot of alteration to our systems, but we don't really know how exactly or a lot of this hasn't been quantified specifically on the impact to these low flows and stream drying especially. And it's important to understand how these low flows and drying is impacting or changing in these environments because of the importance of disconnection in these streams that can be really detrimental to our fish populations. And so understanding natural conditions in both perennial and intermittent streams and how these low flows are different in each stream type can be really essential to how we manage these systems. And using different metrics for these different types of low flows can really help us understand what the biological cues are, as well as how to support more of these species. So today I'm going to be talking to you about how we're quantifying low flows in both perennial and intermittent streams. And to do that, we first need to understand where intermittent and perennial streams occur naturally across California. With an understanding of where these streams occur naturally, we can then look at evidence of changes to these stream types. So are we seeing a lot of streams that should be perennial become dry and intermittent? Or in some cases, maybe vice versa, intermittent streams starting to become perennial. And finally, just looking at how low flows are changing within these different stream types. So first, to quantify where natural streams should occur, intermittent streams should occur, we used a framework very similar to the E-flows, looking at reference gauges across California. Here's where those gauges are located. And when I talk about reference, it means systems that are unimpaired or have very few impacts by humans, both in terms of land use as well as stream regulation. So we use these gauges to look at the number of zero flow days, as well as another low flow metric, the minimum 7-day moving average, which is what you see here. This is discharge across a year, and the 7-day moving average is going to help us understand the lowest point of stream flow in a perennial stream, whereas calculating the number of zero flow days in an intermittent stream is going to give us an understanding of how long we have disconnection in those streams. And so in order to quantify or classify an intermittent stream, we used both thresholds to understand those, but the 7-day moving average always being 0 in those streams wasn't the best metric. So we used the number of zero flow days to quantify how often these streams are drying, and then what would classify a stream as naturally intermittent. If it dries a certain amount of times, a certain amount of years, then we can say that it is intermittent. So to do that, we first set a zero flow threshold of 0.1 CFS to indicate that, yes, that stream is actually drying. We then calculated the number of zero flow days consecutively for each year. And then for each year, a year was classified as intermittent or drying if it had at least 5 days of no flow. So this really ensured that we're quantifying that actually the stream is losing disconnection. But, oh, I have these switched up. They should be switched because this is perennial. But yeah, so For each year, then we classified streams as either intermittent or perennial, depending on that loss of disconnection. So really emphasizing that in an intermittent year, that stream is going completely dry. But then to classify a stream as intermittent overall, so an overall classification, we determined a stream as intermittent if greater than 15% of years across the record were actually being dry. Whereas if it was less than 15% of years that were drying, we would consider that perennial. And that's because often and many times, a lot of drought can cause streams to become dry, but that doesn't necessarily mean that they're intermittent by definition. So we used that as a way to really determine these streams as having drying as a function. So we use these steps to classify natural intermittency across the state. Here's those reference gauges that I showed you before. So to look at an intermittent stream, a stream was classified intermittent, that's this triangle here, and a perennial stream was this square. So you can see how the classification changes across the state. And then the color is going to represent the percent of years that were classified as perennial or intermittent in this case. So in a higher red color, say 90%, is going to be that 90% of years for this gauge actually were drying there. And you can see the variation across the state with a little more drying occurring in Southern California as well as the Central Coast. And we get a lot of our perennial streams in Northern California and across the Sierras. And so what is interesting, though, is that we do see that in terms of the drying that occurs, there's a lot of variability there where in many cases, intermittent streams are not drying every year. So we used this information to create a predictive model that can predict where intermittency occurs, both on the annual level and then use the annual information to classify streams overall. So we used the natural climate and watershed characteristics, input these into our random forest model to then get a prediction of stream intermittent conditions on both the annual and overall classification scale. And generally, this model worked really well, classifying our reference gauges as in the correct classification for the majority of the time. So then in terms of how this information, this natural model could be used, we use this to understand how we might be seeing changes in both intermittent and perennial streams in terms of their classification, just to understand basically an alteration assessment. Where and how are we seeing deviations from these natural conditions? So we used this model that was definitive of our natural conditions, those predictions, to compare to what we're actually seeing on the ground in current years. So we're doing this alteration assessment in the last 40 years from 1980 to 2020 using a different gauge network. So this is the current gauge network, different from what I previously showed you. But in this gauge network, we have both reference and non-reference streams. So again, the reference is those unimpaired streams, whereas the non-reference streams are going to be those heavily impacted or impacted by human conditions, whether diversions, dams, or some kind of land use change that's affecting stream flow in these areas. So what we did was we looked at these streams, the observations there, and classified streams as either intermittent or perennial based on their observations. We then, and so that's what this looks like. That's essentially what we did, just using the observations to what is currently happening in these streams. Then we used our model to understand what the natural conditions should be and compared them to what we're seeing on the ground to understand how this stream gauge network is deviating from what we might expect in terms of intermittency and perennial streams. So here are the results from that comparison from the alteration assessment. But I just want to walk you through the legend here to give you kind of an orientation before I throw everything out at you. So in red, you're going to see a color indicating more drying. So this is that going back to that percent of years. If we had a higher red color, it would mean that we would expect more perennial conditions, but those observations were showing us more years drying, and that is represented in terms of percent. So maybe 100% of the time, things were supposed to be wet or perennial, but they were actually dry every year. And then conversely, moving towards our green colors, this is an expected perennial or expected intermittent stream, but things are more wet in this stream, and that's represented as a percent of the time or percent of years that deviate from those natural conditions. So wetter, drier, and then here again, this is just our intermittent and perennial classification. So for our reference network, this is what we see in terms of changes from our expected natural. Overall, we're seeing that if a stream was classified as intermittent, it was observed intermittent and predicted natural intermittent. So most of our streams in our reference gauge network were not experiencing any or very little change. And most of the time, any type of change in the annual conditions was so small that it didn't meet the threshold to actually change that overall classification. We saw that no streams were predicted to be perennial, but predicted to be intermittent, but changed to perennial. So we had no streams that were moving towards a wetter regime. But we did see evidence that streams that were predicted to be naturally perennial move into our intermittent classification. And so that occurred 11% of the time, although a very small percent, still showing some evidence of drying, even in these natural conditions, conditions. But the story looked very different when we looked at our non-reference gauges. So in these gauges, they're very highly altered, impacted by human conditions. We saw similarly, many streams had no change in their actual overall classification. But in terms of the annual years in which we might see drying or wetting, we are getting a little bit higher of a magnitude in terms of changes there. What was interesting was that we were actually, in some cases, getting changes of intermittent streams becoming more perennial. And that was heavy enough that it changed many of the overall classification. And in looking at this in terms of what might be going on in these streams, we can think about urban discharge, wastewater discharge, as well as dam regulations that might be elevating low flows in many cases. And then when we look at perennial to intermittent streams in our altered or non-reference gauges, we saw a much higher frequency of streams shifting from perennial to intermittent. And not only that there were more streams shifting to intermittent, but that the severity of drying in these streams were at a much higher rate. So a higher percent of years was drying compared to those natural reference conditions. And also to finally kind of understand how streams within each of those classifications, those low flows, were being affected. We looked at trends in our minimum 7-day moving average, as well as the number of zero flow days in our intermittent streams. So again, we used the minimum 7-day moving average to describe low flows in our perennial streams, and the number of zero flow days for our intermittent streams, which is what you see here. And so in our reference streams, we see that there's increase or decreases in our minimum 7-day moving average. So our low flows are getting lower. And then in our intermittent streams, we have increasing zero flow days. So the duration of drying in these streams is getting longer. And these changes in our reference streams really show, because they're not impacted by human alteration, it really shows the impact of climate in these cases. But then when we look at our non-reference streams for trends in both of these metrics, we see varying degrees of both drying and wetting of both of our metrics in either case. And this just goes to show that really you need to go in on an individual watershed scale to understand what is happening in these streams and how both climate and land use are interacting in these ways to affect low flows. So in summary, stream drying and stream intermittency from climate change is prevalent, but our reference streams showed that this drying is occurring at a much slower rate in our natural conditions. So it's a slower process, but again, moving towards some sort of drying. Whereas our human impacts have a variability of effects on both intermittency and low flows. But in many cases, human activities have actually exacerbated the magnitude of drying. And in many cases, we're seeing this drying shift perennial streams to intermittent. And in some odd cases, then we're seeing the effects of human impacts actually causing low flows to be elevated. And so this study can help us understand what impacts are being affecting our low flows. And using this analysis, we are creating new metrics to be incorporated into our eFlows framework. So that's the minimum 7-day moving average, the intermittency stream class, in order to help with some of the alteration assessments, as well as understand how these low flows are impacting some of our populations, as Ethan showed prior. So we're working with the Nature Conservancy to get those incorporated into on the website and hopefully used for use soon. And that's all I have for you guys today. I would love to take some questions.
Thank you, Jesse. Opening it up to anybody that has any questions. Go ahead and raise your hand or drop something in chat. Jesse Maxfield.
Hi, Jesse. Thanks for your presentation. And I did have to step away for a minute, so I may have missed it. Did you talk at all about how groundwater extraction is factored into some of the research that was done?
I haven't, no, we haven't quantified that specifically, but I think when you look back at here, when we look at the non-reference streams and we see a higher impact of stream drying in many of these cases, that is basically a proxy for a lot of groundwater abstraction, because we are losing, with higher groundwater abstraction in many of these cases, we're actually losing the base flow from these streams. And so when we show that there's higher degrees of drying, then that just indicates that there's less groundwater to feed these streams during the dry season. But to your point, we have not quantified, specifically created that relationship. It's very hard to do with the lack of data for groundwater pumping and location of that.
Yeah, that'd be interesting if there's any reference streams in areas where there is data available, showing kind of the trend of increasing groundwater extraction and how that impacts the base flow. Thank you.
Thank you.
Okay, I have a question in chat. Maybe I missed this, but why was 15% used as opposed to some other number like 10 or 20%?
Yeah, great question. We did a little bit of a sensitivity analysis on what was best, and we also looked at what has been reported in the literature. So that 15% was used consistent with other studies, and as well to basically remove streams that are otherwise perennial, but in really heavily drought years are going to actually go dry. And so that just really helped us isolate these differences in flow regimes, the difference between perennial and intermittent. So does that answer your question a little more?
Thanks, it does. So I think the short answer is it's consistent with that number being used in other scientific studies in the literature.
Yeah.
And okay, thanks.
Okay, we'll take one more from chat here, and then we'll move over to hand raising. I'm hoping the streams that have historically been perennial don't get downgraded based on climate change. Do folks sense that reclassifying is being sought? So I would rephrase that maybe a little bit to, is the purpose of this to reclassify existing stream systems?
Oh, sorry, there was some background noise. Could you repeat that?
Yeah. Is the purpose of your analysis to reclassify existing stream systems, or just to get a better idea of how stream systems are changing under climate change or human use?
Mm-hmm. Yeah, I would say both.
Can we make sure everybody's on mute, please?
Okay, great. So I would say, to answer the question, both, because for one, the classification that's done by some other agencies like the USGS has been widely shown to be inaccurate. I think that's largely because if you look at a broader area like the entire US, there's a lot higher degree of perennial streams, and so the intermittent streams often are not represented as well. And especially in California, that's really important because we do have a high degree of intermittent streams across the state. So this analysis was really to help better define intermittent streams in this environment where we do see a higher degree of intermittency. as well as to use this classification to help us understand how these flow regimes can be different in different types of streams, because the way we're going to manage low flows in an intermittent stream is going to be very different than how a perennial stream, the natural conditions in a perennial stream. So that is one element of it, is just to help describe low flows in more detail. And then with that, being able to describe these low flows in more detail, it can really help us give an understanding of how this alteration in the dry season, which, as we know, is a really important, crucial period for a lot of our native species. And so just understanding the dry season better can really help us, I think, manage these really dire season a little better.
So, and building off that with another question in chat. So there's kind of two aspects to the study. One is identifying kind of your reference range of intermittency versus perennial stream systems. And then the second component is expectation. So if you expect a stream system to be perennial and it's showing up as intermittent based on current gauge data or something else, then that's where you're making the connection between, like, maybe there's land use or other activity that is negatively impacting this system, and we're changing it from perenniality to intermittency.
Yeah.
And Kimberly, jump in if I did not describe that correctly.
Yeah, no, that's much clearer, Dan. I sorry my question so poorly framed, but yeah, I think climate change can change the my classification, but if the classification change because demand is up, I would think that we wouldn't want to necessarily go down that route. Am I getting that confused? I mean, that's not the intent here, right?
Kimberly, your audio is a bit broken there, so hopefully by guessing at what you're getting at, still a bit broken.
Yeah, I think you guys have pretty much answered it. I just didn't want things to be reclassified that were impacted by land use or withdrawals or whatever, but because that, I think that we need to continue to, improve our stream flows and not just reclassify things based on that. But that's kind of my concern.
I'm sorry, Kimberly. You're so broke. Your audio is so broken. It's really difficult to hear what you're saying. So maybe if you could put it in the chat if you have a question or we didn't get it right, that could be helpful.
Then we'll move over to hand raised here. It looks like Basam.
Yeah, hi. Thanks, Dan. Audio check again.
You're good.
Okay, thank you. I was wondering, in your definition, Jesse, of intermittent streams here, have you thought about dividing into, or thought about actually the intermittent versus ephemeral as well against the perennial systems? That's one question.
Mm-hmm. Yeah, we looked at that in some detail, and I think what we found was that I think the intermittent streams, excuse me, it's been a while, but the intermittent classification was moved over into intermittent and ephemeral. So essentially ephemeral being defined as like greater than 100 days of no flow. But what we found overall was that the number of streams that were ephemeral was so few. So it was like out of 80 streams that were classified as intermittent, it's only like 15 to 20 were in that ephemeral classification. And it was just really difficult to model natural conditions with that few of observations, as well as just overall kind of isolating this dry period of if we're getting drying, because we're just trying to isolate the drying aspect. It was just much harder to differentiate between those. So we didn't include that here.
Okay. Yeah, I was basically referring to sort of a traditional stream ecology sort of a sense, as in perennial, as in perennial flows, and the intermittent as a more of a seasonal flow regime, and then ephemeral, it's only flows during or right after the good precipitation events, or some in nowadays in the modern environment it could be more of a affluent events. And I was and then also thinking there was a use of temporary and non-temporary waters as well, or temporary flows and things like that. That would be another term, because it's sort of in the confusing is the in this sense of what your definition is, intermittent stream actually includes intermittent of traditional sense plus the ephemeral, as in again the traditional sense of the classification of the stream hydrological regimes. So that's one sort of a question. And I was wondering, and then also the second sort of layer, the sort of a little more complicated question would be, have you considered like geology and the geomorphology of where the streams are located as a factor for prevalence of intermittent streams versus perennial, say like depth to the bedrock or impermeable layers, and then also the like shallow bedrock areas, such as in high mountain regions, or say fluvial driven stream beds, things like that. That could be actually affecting, again, in terms of say where in geographically, specifically the sort of prevalence of some of these different stream types.
Yeah, so to answer your first question, again, the reason we didn't isolate into ephemeral and intermittent was just largely because of the lack of data that describes each of those stream types across the state for reference conditions. We just didn't have enough data to do that. The other thing is that we were just really trying to get at the loss of connection specifically, which occurs in both stream types. So we felt, good about combining them essentially. And then there's also the other classification that's on the eFlows website that uses 9 classification types, and they differentiate ephemeral from the rain-fed and that kind of thing. So here we're just focused on the drying. And then to answer your second question about the geology, yes, I looked extensively at geology. And the one thing that it did kind of improve conditions overall at a very small scale. And that's because the geology data and the layers that are available at a statewide scale are not actually detailed enough to get at some of those differences in geology. So I'll give you an example. There were many streams in Southern California that were classified as intermittent and perennial, and they would often be located, kind of like right next to each other or very adjacent. And when I went in and looked at the geology that was defined for those watersheds, they essentially were the same thing in terms of percent, sand or different types of lithology in those watersheds. And so really kind of what we concluded was it was more about those fine local scale, maybe fractures and faults that are located within those watersheds that are not easily captured in really any data set unless you were to go in and do the field survey yourself almost. Or those data might be available in some areas, but we weren't able to extrapolate over the entire state to use that in a really constructive way.
Yeah, thanks. The sort of the question about the geology was geology also affects the contribution by the springs or groundwater and things like that as well versus the basically precipitation fed type of hydrology. So that's one of the question, the background of that question to you. But thanks for answering my questions.
Yeah. And we do have some of those variables captured in our data. What was most important was like the percent of sand and clay, and kind of like generally the soil characteristics often were a good indicator.
All right.
Thanks.
Thank you, Jesse. Let's see.
Hi, Chris. Did you include groundwater pumping? So we didn't, our alteration assessment strictly looked at the hydrology, the differences in basically changes from our natural conditions. And we used the reference and non-reference gauging network as a good, basically dividing things up into what's occurring from climate change versus what might be occurring from human impacts. Now, within those, we didn't do a full attribution assessment, so meaning we haven't yet attributed those changes to specific types of variables that might be impacting it. So at present, we can kind of generally group these things, but we haven't actually done the scientific work to say groundwater pumping is affecting in these locations. And so, no, to answer your question in short, no, we have not included groundwater pumping. But again, those non-reference streams that are showing a higher degree of intermittency is likely a proxy for groundwater pumping and streamflow diversions.
Yeah, and then just to build up Kimberly's kind of follow up here, the purpose of this effort is to identify locations where something's expected, like we would expect it to be intermittent or perennial to some extent, versus what we actually are observing. And it's more of that. It's not to say that what we're observing should therefore be reclassified as intermittent if it was perennial.
Yeah, exactly. And the point would be to use this as an overall understanding of where things might be deviating from what we would expect. And then going in on more of a local scale to see what's going on in that specific watershed that might be impacting flows in that area.
Great, thank you, Jesse. Any last call for questions for Jesse? All right, seeing none, thank you very much.
Thank you.
Okay, moving up to our next agenda item is just any in-stream flow effort updates that anybody wants to share with the group. It's round robin, so if you have anything you'd like to share, go ahead and raise your hand. Not seeing any at this point. So moving on to our wrap up with the potential agenda topics and presentations for our next meeting. Does anybody have any thoughts on stuff they'd like to present on, or potentially have anybody that they would like to call in as a guest to present? Chris? Chris, if you're speaking, you're on mute.
How's that? Can you hear me now?
Yes, I can.
Okay, good. Yes, unfortunately, I've been having technical issues here and bumping in and out of the meeting, but in the past, I have asked if you could bring up any segues going between Ceph and Sigma for the rollout of the groundwater sustainability plans happening throughout the state. And were you able to do that today? Because I missed a chunk of the meeting.
No, we're still working on that one. If you have any, contacts or, this is one of the things where, we do rely on everybody as participants to also provide those presentations and those connections. We've been working on it as the tech team to try to put something together, but we're not there yet.
Okay.
There's not a direct, application of Ceph within Sigma, and Sigma itself is still a very evolving landscape. So there's not really anything at this point to really present on.
Okay, so the Ceph work group doesn't have let me see if I'm hearing you correctly. The Ceph work group does not have a contact at the Department of Water Resources, the groundwater section on Sigma in order to have this discussion, or are you asking if we or me or I can help develop that contact to have?
No, it's to develop the presentation. It's not that we don't have contacts, it's that we don't really have something to present to the group within the relationship between Ceph and groundwater and Sigma and DWR and so on and so forth. That's more of a longer term agency implementation that's kind of, quite frankly, based on each individual basin of how they're interpreting applying things. So there's just not really something we could just
the problem we're having is
that makes sense. So it's
so
more of a case study. So a case study would be where I would lead you. So if you have a case study in your area of interest and you want to engage your local
I get you.
GSA and stuff like that, and kind of DWR, then that's how that would kind of evolve. But from a statewide perspective, there's not really a DWR opinion or a state water board opinion on Ceph and Sigma.
Yes,
does that kind of answer that?
Yes, it does. Thank you for getting me back on track here. What DWR is doing is making recommendations to the local agencies on how to, because one of the things they're required to do in their groundwater sustainability plans is to avoid undesirable results, such as drying of the streams and dewatering due to groundwater pumping. So healthy flows is something that everyone struggles with in these groundwater sustainability plans. And it just seems like Ceph could help bring some clarity to where they should be going with environmental flows. So yeah, okay, thanks.
Yeah, and Chris, on that point, I think, Ceph outlines an excellent framework to help them work through identifying what those flows might need to be within the targets of the 2015. Again, Sigma is not to exceed in-stream flow impacts from 2015. It's not to restore flows prior to 2015, so it is a little nuanced there. But one thing I do see is it looks like Baruz from DWR is actually on the line, and maybe he has something additional he would like to add.
Yes, can I chime in?
Yes.
Yeah, this is Baruz from DWR. We are in the process of developing a guidance document and 3 topic papers regarding depletion of interconnected surface waters by maybe end of this year, and we will be finishing up the document by maybe early summer next year, and we would provide a lot of help to help guidance to help our GSAs improve their plans and provide better estimates of timing, quantity, and locations of depletions for each GSP. But this is just for Bulletin 118 basin boundaries, because we have to comply with Sigma, but in headwaters we have some kind of recommendations to improve and estimate those depletions as well.
Is that coming out with your guidance, or you mentioned headwaters? Is that piece that you
Headwaters is not that's the problem, because basin boundaries, Sigma or Bulletin 118 basin boundaries are not covering headwaters, especially like the Russian River basin. We have a ton of wells upstream of the aquifer boundaries, but those are sedimentary or volcanoclastic rocks, and they can be classified as sedimentary rocks. But this is a question. We haven't decided to exactly change the basin boundary, but it's case by case. For some adjudicated basin boundaries, it's impossible, but for the areas that we don't have problem, we can change boundaries, but it based upon the GSA's request.
You know, this is,
As I'm not, if I'm wrong, please correct me.
No, I appreciate what you were saying there, and that you are speaking right now. And I'm wondering if Daniel, if we can actually have you as a guest speaker to go into this more, because I know we don't have enough time.
Yeah, we don't have, maybe next year.
Next year.
Because
maybe next year. I'll take that. I'll take it. That sounds good.
Okay. Yeah, you can put Daniel can put it on action item a couple of months after 2020, January 2024. I will give you updates.
Oh,
no
great.
problem.
Great. Thank you so much. I appreciate this.
Bruce, the group would obviously love to hear about any updates related to that effort. So if you just want to reach out to me when you guys get closer to being ready to present, that would be great. And we'll get you on the schedule.
Sure. Thank you so much. Sure.
All right. Any other thoughts for future agenda topics? All right, hearing none. So that wraps up our meeting for today. Thank you all for attending. I do see a note in chat. Let me just check that before we close out. It looks like there is one. Oh, there's a couple in here. Sorry. Flows and toxic algae, nutrients, etc. Relationship to that, as well as, and we discussed reduction in demand might help along with the toxic algae and sickness in sea life and others. There is some work being done on that, but it's kind of some of those relationships, not just with algae, but also macroinvertebrates. We're working on developing some of those relationships. We don't have anything to present at this point, but as soon as we have something to present, we will happily present it, and also reach out to our water quality side and see if they have anything that they have put together along those relationships that they could maybe come and guest present at one of our future meetings, Kimberly. So I'll add that to my notes. I'm assuming you're looking for relationships between flows and toxic algae. Kimberly. Okay. And then just one other comment that the SEP technical team has been thinking of ways that SEP and tools can be developed to help inform Sigma and Interconnected for meeting up in the future. And then Eric is going to help me coordinate with some of the algae work that's being done and the flow relationship. Anything else? Chris, did you have another question? Your hand's still up. I'm not sure if that's legacy. All right. Well, thank you all for attending, and we will see you next quarter. As always, if anything comes up and you have any things you would like to potentially present for a future meeting or to flag for future meeting topics, feel free to email me or any of my team. So thank you very much for your participation today, and we'll see you next quarter.
Thanks, Dan.
Thanks, Dan. Great meeting.